Okay, well, it is really exciting and to have Sherry Gong from Stanford, and she's going to tell us this evening about non-orientable link cobordisms and torsion and Floer homologies. Go for it.
Okay, thanks. Okay, thank you so much for coming to my talk. I'll be telling you a little bit about some bounds for the structure of non-orientable link cobordisms. So we're going to be studying non-orientable link cobordisms, smoothly embedded, not necessarily orientable cobordisms between knots. And so one of the sort of quantities of such cobordisms that we'll sort of be using is this notion of the non-orientable genus. So the non-orientable genus of a cobordism is defined to be 2 minus the Euler characteristic minus the number of boundary components. So for a cobordism between knots, this just ends up being the negative of the Euler characteristic. So various topologists have studied this quantity for non-orientable cobordisms, giving bounds for it, for computing, giving bounds for how much genus, non-orientable genus, like a cobordism between two knots has to have, and also computing the minimum genus of a non-orientable surface bounded by a knot, like what the minimum genus of such a surface has to be. But we're actually going to be studying a slightly different question. We'll be studying the question of if there is a cobordism of a certain genus, how complicated does it have to be? By this, we mean in terms of minima, maxima, and saddles for a Morse decomposition of the cobordism. Okay, sorry, I forgot to say, by we, I mean, this project is a joint project between myself and Marco Marengon. And yeah, okay, so we're going to be studying, given that there's a cobordism of a certain genus between two knots, how complicated does this cobordism have to be in terms of minima, maxima, and saddles of a Morse decomposition? Okay, so let me give some background. So for oriented knot cobordisms, Juhasz, Miller, and Zemke proved an inequality relating the number of local maxima and the genus of a cobordism between two knots to the torsion order of a version of knot Floer homology, and that's for orientable cobordisms. And our result is basically just a non-orientable analog of this. So we're just doing the same things as what they did, but with non-orientable cobordisms. So in order to do that, we're going to use different Floer homology theories from what they used, because we're going to be choosing ones that behave well for non-orientable cobordisms. And we'll be using a version of knot Floer homology and a version of instanton Floer homology that induces maps for non-orientable cobordisms that behave well, by which I mean they don't just vanish. They don't just give you zero. So the version of knot Floer homology we'll be using is Oathvath, Stipschitz, and Szabo's unoriented knot Floer homology, which denoted HFK prime. This is a module over the polynomial ring in one variable over the field of two elements. And we want to use this because it was largely, we're going to be using some results by Haofei Fan that say that you can, if you have an unorientable cobordism with some extra data that I'll mention a bit more later on, it induces a map on this unoriented knot Floer homology. And then one property of this is that, okay, so this is a module over FU, and the torsion part of it is going to be killed by some power of U. And we define the unoriented knot Floer torsion order as the minimum power of U that kills the torsion part. Okay, and then we're all of our results are going to be in two parts. There's going to be this knot Floer homology version and an instanton Floer homology version. So the version of instanton Floer homology we'll be using is Kronheimer and Mrówka's instanton Floer homology with local coefficients, which is denoted I sharp of k. This is a module over a Noetherian domain S that has a special element P. So more specifically, the ring S is going to be constructed as a quotient of the ring of Laurent polynomials in 4 variables over the field of 2 elements. And P is just like a specific element that can be written down, like I guess I've shown you like how to write it down in terms of like, it's the image of this element that you can just explicitly write down in terms of the TIs. And I guess like, let me just sort of briefly describe what these elements mean. So the instanton Floer homology of a link in S3 is sort of, it's defined as the homology of a chain complex where the generators of the chain complex are flat connections in a singular bundle, like flat connections in a singular bundle over S3 with singularity at the link and also at this like extra theta web that we're going to add that's sort of taken to be far away from the link. So you have like your link in some ball and then the theta web outside. And then we're looking at the instanton Floer homology with local coefficients. These local coefficients correspond to a local system that's coming from, so it's a local system is basically some function to like S1 from this space of like flat connections. And then the local coefficients we're going to take are going to correspond to a local system coming from taking holonomy along the components of the link and the 3 arcs of the theta web. So T0 corresponds to the holonomy along the link, and T1, T2, and T3 correspond to the holonomy along the 3 arcs of the theta web. Okay, so we're going to be restricting our attention to specific domains S, so not like any quotient of this Laurent polynomial ring. And we're going to choose S in such a way that this I sharp k, this like functor is going to be, it's going to be functorial for non-orientable not cobordisms. And in order to capture the information we want about these non-orientable cobordisms, we are also going to choose S so that these cobordisms, so that like we can define maps from cobordisms with more complicated singular bundles. Specifically, we're going to take singular bundles represented by surfaces omega whose boundary like sits on the cobordism. So there's like surfaces with boundary, and we're going to take these surfaces to like only intersect the cobordism at the boundary of the surface where it intersects cleanly. Specifically, what it actually means is that we want S in which T0, the element T0 maps to 1. So it's been shown that, so Kronheimer and Mrówka showed that in this situation, the torsion part of this instanton Floer homology is going to be killed by a factor of P. And then we can take the torsion order of a knot to be the minimum power of P that kills the torsion. Sorry. Oh no. What happened? Yeah, okay. Okay, so now let me tell you about Marco and my main result, which is analogous to the main theorem of Juhasz, Miller, and Zemke's paper. So the main result says that if K1 and K2 are 2 knots in S3, and there's an unorientable knot cobordism from K1 to K2 that has capital M local maxima, then the order of K1, the torsion order of K1 is bounded by the maximum of the torsion order of K2 and M plus the like non-orientable genus of the cobordism. Okay, so as a remark, the same theorem, I mean, I stated it for an unorientable not cobordisms, but the same statement is actually going to also be true for orientable cobordisms. But in the orientable case, the result actually follows from the exact same argument of Juhasz, Miller, and Zemke's paper, because their argument primarily uses a tube cutting formula for knot Floer homology, and the version of knot Floer homology and instanton Floer homology we're dealing with have actually like basically the same formula for tube cutting for orientable cobordisms. So the only actual subtleties in our argument are dealing with like the non-orientability of the cobordism. Okay, so since our argument is like pretty similar to theirs, let me just sort of tell you a little bit about the proof and sort of like, yeah, okay. Let me just tell you a little bit about the proof. So like we start by doing like similar to what they did. We divide this cobordism into like, we decompose it into pieces. But like sort of the only difference here with Juhasz, Miller, and Zemke's thing is that we have to keep track of this non-orientable piece. So if a cobordism, so for a cobordism between two knots that has little m local minima, b saddles, and capital M local maxima, we can divide it in we can do it in stages where first you do the like little m local minima, then you do a bunch of saddles, and then in the end you have the capital M local maxima. And so like this is sort of a picture of what we're doing. So first you have these little m births, and then you have these like sort of these like birth canceling saddles that sort of cancel the birth so that you end up with a knot again. Then you have a bunch of additional saddles. So we divide this into the additional saddles that are orientable with respect to K1 prime, which is the knot after you do the birth canceling saddles, and the one which is unorientable with respect to K1 prime. And you can always make sure that there's only one of these additional saddles which is unorientable with respect to K1 prime, because if you have like several that are unorientable, you can like slide one orientable one sort of over another one to make it orientable. So like actually, you know, it is true that you can just have all these additional orientable ones followed by like an unorientable saddle. And then you have these death canceling saddles. So those are the saddles that sort of break off components corresponding to the deaths. And then you have the deaths. So this is like just similar to their decomposition, except that we have to keep track of one unorientable saddle. Okay, so now let me just tell you like briefly Juhasz, Miller, and Zemke's argument, and then like we'll see what we did that's like a little bit different. Okay, so the structure of our argument is pretty similar to theirs. So what you do is once you have this decomposition, you take the same cobordism, but you run it backwards. So from K1 to K2, and then you run it from K2 back to K1 by just doing like time reversing everything. So I'm just going to call that like sigma bar, or the mirror of the original cobordism. And then what you want to do is relate this cobordism to like the cylinder on K1 by doing a bunch of tube addition and tube cutting moves. So what like specifically for each band, so specifically like for each death, you sort of can add a tube from like the death to the mirror of the death. So that sort of cancels the death. That's like as if you didn't do this death. And then that's like a tube addition. And then for each of these bands, you can sort of do like a tube cutting, like the band and its mirror basically forms a tube, and then you can do a tube cutting. So, and then sort of once you've done that, what you end up basically getting is just the cylinder on K1. I mean, there's also a few extra like spheres that you get corresponding to these births, but that like doesn't actually matter. So really like what you end up getting is a cylinder. So that means that in order to like, if you can control what happens with like tube addition and tube subtraction, then you can control the map induced by this cobordism based on the map like induced by the cylinder, which is just the identity. So let me just tell you about like orientable tube addition and removal formulae. So again, I'm just going to start with the orientable case. So for not Floer homology, if you have a cobordism sigma prime, obtained from sigma by the addition of a tube whose feet are oriented equally on sigma, then the map induced by sigma prime is going to be basically u times the map induced by sigma. So adding this tube, any like addition of a tube, just gives you like an extra factor of u. And then in the instanton case, there's like a general formula for if you have a map, like if again sigma prime is basically the same as sigma except with an additional tube, and here we're taking the tube to have feet at points p and q. So in the instanton situation, there's like a little bit more going on. You actually it's actually the case that you don't just get maps from cobordisms, you also can like induce maps from like dotted cobordisms. So that means cobordisms with a few extra marked points that are given an orientation. So then like in that case, the map induced by sigma prime, where sigma prime is sigma with like an extra tube between p and q, the map induced by sigma prime is p times the map induced by sigma plus the map induced by sigma with an extra dot at p and the map induced by sigma with an extra dot at q. So if p and q, these 2 points are oriented the same and are also on the same component, then these last 2 terms cancel each other because they're equal to each other and we're working in characteristic 2. So you basically also end up getting this, that it's just like the same as sigma, but with an extra factor of p. So then in the case where you have an orientable cobordism, then you're like the argument is basically finished because you have like, so you basically, if you consider this cobordism that comes from the original one with its mirror and then with this extra tube for every depth, this cobordism, you can cut capital M tubes to turn it into sigma bar composed sigma, or you can cut little b minus little m tubes to turn it into the identity. So that means that p to the m times the map induced by sigma bar composed with sigma is p to the b minus m times the identity. Because like the map like here on both sides is the map induced by this cobordism with these extra tubes. And then the same is going to be true for the HFK situation. Okay, so then the question is, what do you do about the non-orientable piece? So the problem with like if you just try to do the exact same argument is that for a non-orientable like band addition, what often happens is that the map induced on like at least let me just do the instanton and not Floer cases separately. In the instanton situation, the map induced is usually going to be 0. So for example, if you just take the RP2, like a twice punctured RP2, so that's like a punctured Mobius band, as a map from the unknot to itself, like just a very standard, like, you know, you just take this unknot and then you like the way I've drawn it, and then you just sort of add a band in this little centerpiece to turn it into this other unknot. This map is like the map induced by this twice punctured RP2 is actually just the 0 map. And that's sort of very bad because like the whole purpose of this is to count factors of p, but if your map is 0, like that really like does not, now you just get no information. So the way to sort of fix this is by considering a different singular bundle. So this like cobordism I've been using somehow like a standard singular bundle, but what we can do is consider, so for instantons, not just like, so you have cobordisms with like the standard singular bundle that's like singular at this, like at the cobordism, that induces a map, but you can also consider other singular bundles on the same cobordism, and the singular bundle is going to be we're keeping track of it via a surface that has boundary on the cobordism. So, so like in this case, for example, you could take like, sorry, let me just take a step back. So in order to induce like a map on instanton Floer homology, you need a cobordism with this extra singular bundle data. The singular bundle data is usually taken as this sort of surface in S3 times I. You can take it to have like boundary, but the boundary has to be on the cobordism. And it has to meet the cobordism sort of cleanly at a boundary. So it has to like sort of meet like sort of transversely, like basically like this. And also the other sort of requirement is that this extra surface can only intersect the cobordism at the boundary of the surface. So it can't have random intersections inside. So what we basically want to do is say like to choose, like if you choose a surface, like in the case of this this unknot, RP2 from the unknot to itself, like if you choose the surface to be basically like this, like I have this picture of this unknot, right? Like it's sort of got this band in it. So where I'm gonna add a band to make my RP2. So this band kind of divides this unknot into like, it has two wings. So if you basically take a surface that like is the disk that's bounded by one of the wings, and then like have it, but the surface like sort of juts out a little bit, like, so you see it's just bounded by one of the wings and then juts out with this little disk. Then this surface, like the map induced here, is not going to be zero. And so, and in fact, like if you do this as like the map from the unknot to the RP2 and you do the reversal like we've been doing with all of our bands, like this actually behaves, this surface, the map induced by this cobordism with this extra surface is sort of exactly like what we want. It behaves the same way as like if you just had like an orientable tube without this extra surface. So basically, this is the idea of what we want to do, is like to add this extra decoration. But so what we do then is we take our knot. I guess in this picture I've still drawn the unknot, but you could imagine like it could be any other knot, right? This dotted part, it doesn't have to be the unknot. And then you basically take a Seifert surface of like one of the wings of the knot plus this little disk, and then you basically just take that to be your surface. There's like, so here this is a picture of like, I have the blue and pink are the two wings, and then like the green is a diagonal of the band. So really what you're doing is taking a Seifert surface of the pink wing and the green segment, which form a knot themselves, and then you add this little like half disk piece. One problem with just doing this straight up is that that could still intersect your cobordism elsewhere. Like, for example, if I just took a Seifert surface of this piece, then like it's possible that the rest of the knot intersects the surface. But it turns out that that's sort of okay. Like you can sort of get rid of that by just sort of, if it intersects a surface, it has like positive and negative intersections. And then you can sort of twist this like blue band along the end to like sort of cancel out the positive and negative intersections so that you have the same number of positive and negative ones. And then you can basically like any like positive and negative intersection, you can just take a tube that sort of cuts out that piece. So it makes your surface omega have higher genus, but that's sort of okay. But you're like getting rid of the intersections with B. Then once you've done that, you have this like, you get this surface, and then you consider the map induced by this surface, by the cobordism with this extra surface. And then you do the same thing as before. You take that, like this cobordism is a band, right? You do the reverse of the band with the sort of mirror of this like omega surface. And then once you've done that, it turns out that like, so now you have still this unorientable tube, like this tube that's sort of, whose feet are not oriented the same on the rest of the cobordism. But this tube sort of has these like, has the boundary of this like extra surface data, this omega is sort of going down the tube in a way such that like the tube is in the middle, it has like a little flip. You can think of it as having a flip if you want to think of the ends as being oriented the same. And then this like, this like pink lines are sort of going through the tube. And it turns out that like, if you, in that situation, you actually have the same neck cutting formula, the same tube cutting formula as like without the, as basically without the, as basically without like this unorientable, like this like like orientation breaking flip. And then you basically can run the same argument as in the orientable case. Okay, so let me just also briefly go over what happens with not Floer homology. So for HFK, I guess this should have been HFK prime, but in order to induce a map in not Floer homology, you have to sort of have, you basically, you don't just have a cobordism, you have a cobordism with like a little bit of extra data, and the extra data basically consists of some set of arcs where the boundary of the arcs are 2 points on each end of your cobordism. So like you have knots on each end, and each knot has 2 points on it, and then you have these arcs across it. So like here, these arcs are drawn in red on this picture. And the thing about these, the property that these arcs have to satisfy in order to induce a map, a well-defined map, is that they have to divide the cobordism into orientable pieces. So in the case that your cobordism is already orientable, you can just take a pair of parallel arcs just running from one end to the other with like sort of no actual topology going on in this little piece that you're cutting off because it's just a strip. And it's like, since everything's orientable anyway, it's okay. But in the case of like your surface is like non-orientable, like if we have this extra sort of tube whose feet are not oriented the same on the cobordism, then in order to get this get these arcs to like actually induce a map, the arcs have to go through this extra tube. So in this picture, like the big vertical cylinder is supposed to be K times I, so that's like the knot times I, and then it has this extra tube on it that has a little flip in the middle. This little blue twirly symbol is meant to denote the flip. So you're thinking of it as like there's this flip in the middle, and then your like arcs have to go through this little tube with a flip. Okay, so then like once you've done this, it turns out that like if you have a tube that has a flip in it with like arcs going down the ends, then the flip map actually just induces the identity. So basically this picture like induces the same map as without the flip. So now it's like orientable. But there's still like a little bit of a problem here in that these arcs like somehow, even though we've now made the cobordism orientable, the arcs are still going through this like extra tube, which we don't want, right? Because in like we would like for the arcs to just go from one knot to the other without doing anything, without intertwining these extra topology in any way. And so originally what Marco and I would do, like decided to do for this, was to add sort of an extra tube, and as a result of that, all of our inequalities in our first version of this paper had this extra factor, these extra plus ones. But Ian Zemke reached out to us and gave us a proof that did not actually need this extra tube. Oh, oops. Okay. So his argument, he basically said you can actually get rid of the problem of the arcs going through the tube by doing this bypass argument. So what that means is you take like a region, like basically the region, in this picture, it's the region that's circled by the blue circle. And then you can sort of replace these like the 3 arcs inside with different sets of 3 arcs. And so that basically replaces this upper cylinder with these 2 cylinders on the bottom, where you can see that in this picture on the left, the arcs are no longer going through the tube. And then the picture on the right, you can just sort of like deal with by a grading argument, and you show that the map induced by the picture on the right vanishes. Okay, so then I guess that sort of concludes this like outline of the proof. So I guess the other things I wanted to tell you about are basically some corollaries of this. So these corollaries are also basically analogous to the ones in Juhasz, Miller, and Zemke. So one of them is about non-orientable ribbon cobordisms. So for a not cobordism, we call it ribbon if it has no local maxima. So in particular, a ribbon concordance is a concordance, which is also a ribbon cobordism. And so sort of immediately from our theorem, you can conclude that if you have a ribbon cobordism, orientable or otherwise, the torsion order of K from K1 to K2, then the torsion order of K1 is bounded above by the torsion order of K2 plus the non-orientable genus. This is just, you apply the theorem and set capital M to be 0. And this is true in both instanton and HFK. Another result is about the band unlinking number. So the unoriented band unlinking number of a knot is defined as the minimum number of band surgeries that turn K into an unlink. And then you can show that this number is bounded below by the torsion orders from this theorem. Basically, this is because, like, if you just cap off some extra ends of the unlink, this like unoriented band unlinking number basically turns into the number of deaths plus the non-orientable genus. And then I guess, and then the other corollaries I want to talk about are all about this this thing that we're calling the refined unorientable cobordism distance. So the standard cobordism distance between two knots is given by twice of the standard slice genus of K1 connected sum with the mirror of K2, where K1 and K2 are the two knots. So like, and this is not a distance on the set of knots, because concordant knots will have distance 0, but it descends to a well-defined distance on the concordance group. So in Juhasz, Miller, and Zemke's paper, they basically gave what they called a refined version of the cobordism distance. And so let me just give like a refined version of the cobordism distance for like sort of an unorientable version of that. So you can, for a cobordism with little m local minima and capital M local maxima, we can define, like, let's call the norm of sigma to be the maximum of little m and big M minus the Euler characteristic of sigma. And then given two knots, K1 and K2, we define the standard unorientable cobordism distance between K1 and K2 as the minimum of the negative of the Euler characteristic of a surface from K1 and K2, where we're varying this surface over unorientable connected cobordisms and all genus 0 orientable cobordisms, because, like, I guess we do want to include the concordances, and those are sort of necessarily orientable. And then the refined the refined unorientable cobordism distance is basically the same as that, but you use this norm of sigma instead of minus the Euler characteristic of sigma. So it's sort of like, it's going to be like larger, right? Because you also like want to keep track of the minima and maxima. Okay, so as an immediate corollary of the theorem, we get that the refined unorientable cobordism distance has, like, it is lower bounded by the difference in torsion orders between K1 and K2. This is because you can show that the torsion order of K1 minus torsion order of K2 is less than or equal to M plus gamma of sigma. This is because if you move the K2 to the other side, this is because M plus the torsion order of K2 is at least the maximum of M and the torsion order of K2. And then the second inequality comes from running this argument backwards. So you view it as a cobordism from K2 to K1 instead. So then the maxima become minima. You swap maxima with minima. And then what we can conclude from this is that the refined unorientable cobordism distance can be, like, we construct knots to make it show that it can be like arbitrarily different from the standard unorientable cobordism distance. So to do that, we're going to do some computations. So the knots we construct are going to be connected sums of these torus knots T and n plus 1 with mirrors of torus knots like this. So to do that, we compute the torsion orders for these knots. You can do that because torus knots are L-space knots. You can sort of read off everything here from the Alexander polynomial to conclude like that what the torsion order of T and n plus 1 is. And you can also sort of compute the torsion order of connected sums. It's the maximum of the torsion order of each knot. And then the torsion order of like the mirror is the same as the torsion order of a knot. And so like this is how we're going to sort of show that these like that refined cobordism distances can be like large, while when like standard cobordism distances are not, because somehow if you connect summing a knot with its mirror, like if you connect a knot with the mirror of like another knot, then like somehow the like standard torsion, the standard cobordism distance is somehow getting canceled, but the refined one is not getting canceled because like the connect sum takes the maximum of the two. So specifically, like the corollary is that for any gamma and m, there is a knot whose standard unorientable torsion cobordism distance to the unknot is gamma, but the refined one is at least gamma plus m, meaning that any cobordism between the unknot and this k gamma m that has like basically that has like a non-orientable genus equal to gamma has to have at least little m local minima. And then here the knot that we take is basically the connected sum of T 2r minus 1 2r with T 2s minus 1 2s, where we compute these torsion orders of these knots using these formulae. And I guess that's all I had to tell you. Thank you for the invitation and thanks for listening.
Thank you very much, Terry. Okay, so would anyone like to ask questions of Terry? That's how this works.
Yeah, can I, hi, this is Melissa. Just to review, I think I flipped over it. What is the notion of distance again?
Oh, yeah, so the distance is basically like the standard one is sort of asking like how much topology has to happen in a cobordism between them, and the refined one is sort of how much topology and like extra data about the number of minima and maxima.
Okay, so I'm wondering, I mean, this has to be related to a knotting number as well, right? I mean, I mean, okay, so I'm thinking about how there's like the relationship between how much topology is between two things and also like how many crossing changes you need to do to get from one knot to another. And I think there should be a bound in one direction, like just thinking about
yeah, I mean, I guess to get from like these crossing changes all involve topology, right? So
exactly. Yeah.
So I would imagine that would be related. Yeah.
Okay, so I mean, again, you could repeat kind of what Melissa was saying, or what your answer, Melissa, is that the standard one is just about the abstract topology of the surface, and then the refined one is about how it's embedded, right, in four-dimensional space, right? So, so this may not be a fair question, but is there any way to use this to say anything about closed embedded surfaces in R4 or any four manifold? So I mean, you know, that they're, let's say, a non-orientable one, so they're cobordisms from the unknot to the unknot, which is boring, but I mean, it's probably a standard question. Can you take any of these cobordism type invariants and then use them to actually say something about two-knot theory or that sort of thing, right?
Yeah, I'm not sure, maybe.
Because I mean, you're sort of getting at a little bit of the knottedness of the cobordism.
Yeah, I mean, you are sort of getting at like how this cobordism is embedded, right? Like, so like, yeah, like in this case, we're saying that somehow if you have like, if you're capping off a knot, like you can't just like cap it off without like having at least some local minima. You have to have like a lot of local minima in your cap.
Which is sort of related to like minimum numbers of generators for the I1 of the complement of the surface, right? I'm not sure.
Yeah, I'm not sure.
Other questions? Okay, well, let's thank Sherry one more time, and then I'll stop the recording.
Thanks, Sherry.